All right. Thank you. Um, so I have made some lecture notes for everyone to follow along, so you can actually um, use your phone. I think I'm echoing. I think it's fine. So if you navigate here, then you can, if you want, you can download the PDF. You don't have editing rights, but if you find any typos, it's still a work in progress. Uh, but it should give you kind of material that you can use along the lectures. And if you download the PDF, you can decide to make notes on that PDF or write your own notes. It's up to you. Um, there's also a bunch of questions in that set of lectures. Um, we're still deciding whether we're using all of those questions for the tutorials, or whether we are going to just pick a few, because there's quite a number of them. And what we do want to include is you experiencing a little bit of actual um, 20 sorry CMB anisotropy spectra. So for that, we will ask you to install CAMP, or I guess CAMP or class. Does it matter? Will? Yeah, probably use CAMP, but I guess if you prefer class, then you have to convince Will. That's okay. So we might provide you with some instructions. I mean, the easiest way is just navigate to the CAMP webpage, and there is some instructions. Now, of course, maybe not everyone has a laptop. If you don't, make friends. Yes. So if you haven't done it, then it's another assignment. Um, okay, so I do want to give a little bit of context about this. So when I was asked to give these lectures about cosmological tests of fundamental physics, obviously I think cosmological tests maybe is more clear, but then it came to mind, like, what do we mean by fundamental physics? Uh, is that something that we decide that something is fundamental, or is there some more maybe rigorous way of defining this? Maybe somebody wants to tell me what they think when we say fundamental physics. Anyone? That's a good question. Yes, but do you have an idea what are, when we say, because we the point I was thinking about this, and we write this in every single proposal that we submit. We say are doing fundamental physics, but really, do we know what we mean by that? Okay. Okay, so it differs on the field. Could there also be some? Well, if there's no fundamental rigorous way to define fundamental physics, is it maybe also time dependent? Let's say that. Do you think that Isaac Newton thought he was working on fundamental physics? Probably, yeah. Do we still think that's fundamental? Sure. Just period. So then cosmological tests could be anything. Okay. Okay, well, maybe that's true. Well, if does everyone agree, because we only had one vote, but maybe somebody else has a different notion of what fundamental would mean? Okay, well, my view on this, and there's no ground truth, I think, but the way we think about these things is I think, represented by a figure that's in the lecture notes, which is called this cube of physics, which connects different fields in terms of fundamental constants. And so we do have an idea. I think many people agree that there are fundamental constants. Yeah, and so somehow If we turn these off or on, or whether they become relevant or not, I think tells us in what part of the physics cube we are, and therefore maybe how fundamental something is. Is that maybe as rigorous as we can get? And so what I point out, I think that the fundamental constants that we typically have to worry about are like h bar, g, and c, right? And so I think that perhaps the most fundamental we can ever hope to work on would be when all these constants are relevant. KB also maybe, yeah, but maybe not in the physics cube. KB doesn't necessarily appear, but yeah. And so now the question becomes, when are all these three relevant? Just make a guess. Okay, make a guess. Right. 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 So I think that typically we'd say, okay, these are all relevant when we are in this quantum gravity regime, right? And so now it turns out that when are we in a quantum gravity regime? For example, very good. But my talk is not about black holes, so there's only one other option, I think. Early universe. Very good. Yeah, it's either A or B. So then it would be early universe, okay? Okay, so now I think the circle is complete. So fundamental physics is something we can test with cosmological observations. In particular, the things we want to learn are those processes that happened in the very early universe because they touch upon the physics where all these three fundamental constants are not negligible or cannot be ignored. Okay, so that's just a little philosophy on the title of this. Took 10 minutes. Okay, good. But let me just give you a brief outline of what I'm going to talk about. So this would be the topic, but in terms of the setup of today, so I'll just have an introduction, hopefully somewhat somewhat light. I really want to try and give you a context before I dive into detailed equations and whatnot. I might also skip some things, but then hopefully the lecture notes will provide the necessary background. And there's a long list of potential references that you can navigate through if you want. So the introduction will concern the cosmological principle. And particularly in the context of cosmological correlation functions, and I'll explain what those are. Correlators. Okay. And then I'll continue with explaining the physics, the background physics of an expanding universe. Which is relevant, obviously, in this course. Followed by what happens to, particularly what happens to photons. And the reason why I'll talk about photons is that there's limited time of the stuff I can discuss, but I'll mostly focus on the CMB as a cosmological observable. Yeah, in principle, I could also talk about large-scale structure, any tracer of density or of the potential. But I'll talk about photons because I prefer to talk about the CMB. Yeah. So. Okay, and then this is day one, and then tomorrow I'll talk about perturbations. Right. So that really will involve a little bit more equations. And on Wednesday, I'll talk about inflation. On Thursday will be Gaussianities. And then on the last day, I'll talk about non-Gaussianities. So I would have loved to talk about non-Gaussianities from the start, because I think that's the most interesting bit. However, I think that it does help if you have some understanding of everything that precedes this, and that requires me to go through all these steps. Okay. Let's move on. So, given our kind of conclusion that the early universe would be a good testing ground of fundamental physics, and the fact that I already mentioned inflation, so in some sense, of course, who knows about inflation, cosmological inflation? Okay, quite some people, good. But some people don't, right? So that's why I really want to make sure that everyone is following this. But one thing, of course, about inflation is that in some sense, it's already new physics, right? So if it indeed inflation happened, it's already new physics. And so let's say we have now made that conclusion that this is new physics. How do we actually test models of inflation or any model of the universe? And thereby, right, synonymously, fundamental physics. And the answer to that, so how do we measure, let's say, okay, what observations? Or what type of observations should we make to learn about the early universe? Okay. Anyone an idea? What should we try to measure? Gravitational waves. Photons from CMB. But what type of observables? Like if I just have a detector, like correlations. Correlations. Does everyone mean but what we mean by correlations? They're correlated, right? So I would say, generally speaking, what we try to measure is statistical properties. Yeah. So that would be, so the thing we want to, so if this was my question, I would say answer statistical. And nomenclature-wise, okay, so I could measure, for example, the mean temperature of the CMB or the mean density of galaxies in the universe. It turns out that that tells me very little. So we have to go beyond the mean, and we can look at the variance. And at the field level, this is known as a two-point correlation function, and the Fourier equivalent of the two-point correlation function is the power spectrum. And we could go on and on, right? We can go on to the three-point correlation function, and the Fourier equivalent of that would be the pi spectrum. Okay, so that's what we hope to measure. And from these correlation functions, or these n spectra, what we can, so there's, I guess there again we can say, okay, what things do we want to measure? Well, it turns out that, for example, from the power spectrum, what we want to deduce is the overall amplitude and the scale dependence, right? So from that, so if you consider the power spectrum, I mean, I'm writing all these things down. If they don't mean anything to you, that's fine, because we'll go through these in some more detail later on. I can measure the overall amplitude, which is typically related to AS, and then scale dependence, which is denoted as NS. And S here in this case stands for scalar. Okay. But Now, if the fluctuations that, well, okay, so now maybe I should have stepped back. Because we are looking at correlation functions, we have to look at fluctuations. We cannot, at the field level, we're looking at a field that has a value at every space-time point. And so in principle, if the distribution associated with that field is Gaussian, then everything that you can learn about that field is hidden in the power spectrum. If I ask you, okay, well, what about the bispectrum? What's the bispectrum for a Gaussian field? 0, very good. So you cannot, well, you shouldn't measure it. Well, you can measure it, but then you find it must be Gaussian if it's 0. What about the trispectrum? The 4-point coordinate? 0? Well, it should be proportional to the power spectrum squared. Now, it means that the information hidden here is all inside the power spectrum. So if it's Gaussian, it's all inside the power spectrum. That means that to learn something more about the early universe, if we had only these two measurements, it would be quite limited. So one other thing is to say, this is what we want to measure, plus a potential detection of, for example, primordial non-Gaussianity, right? So is primordial non-Gaussianity 0, right? Or not equal to 0. But the same thing as was mentioned before could be gravitational waves, right? So we haven't detected primordial gravitational waves, but if we would detect that, we would learn something about the early universe. So the other thing that you could think of is primordial gravitational waves. Okay. And so this, in some sense, will be the topic of this lecture series. Yeah? So if we can measure all these things, what did we learn about the early universe, and how does that relate to fundamental physics? Any questions about that? Okay. So in my lecture notes, I do not have a figure, but I do think it's useful to have a figure. So let me just sketch a very classical view that you might have seen in many different talks about what the universe, or what we know about the current state of the universe and its history. So if we assume that somehow the universe started out in what is called an inflationary phase, where it grew significantly in a very short time period, and this happened roughly around 10 to the minus 33 seconds. And after that, you had the inflaton degrees of freedom being transferred to matter and radiation. You get this very hot, dense plasma. The universe grows, does grow, but not as fast as during inflation. And at some point, the universe cools sufficiently for hydrogen to recombine. So the protons and the electrons recombine, and that's when you have the photons being able to free stream. So before that, they are always tightly coupled to the plasma because they Thomson scatter off of free electrons. And so you have a moment where you produce the C and B. So this is really what's generally referred to as the surface of last scattering. So this is when photons in the universe last scattered. Of course, it's not entirely true. There are some photons that will scatter after that. But by and large, most photons last scattered at that moment. And this is roughly around 300,000 years. Now, of course, once photons decouple from the plasma, matter can now freely fall into the gravitational potential, which has been mostly driven by cold dark matter. So cold dark matter plays an important role of setting the initial large overdensities, large potentials, so that the baryons, which are coupled to the photons, can fall in these potentials. But before that, there's a very long period where there's no bound objects, no collapsed objects, and this is generally known as the Dark Ages. Yeah, so there's a period known as the Dark Ages. It's literally quite dark, right? There's a period roughly between redshift. Well, this roughly corresponds to redshift 1100. Yeah, and then the dark ages last all the way up to redshift. Well, that depends a little bit on your model, but somewhere between 30 and 50. So that's when you have the end of the dark ages. Draw this like this. Where there's no collapsed objects, it's still something that we can observe, but only in a narrow window starting from redshift 200. And this is when you have the so-called 21 centimeter line tracing the structure in the universe. So from redshift 200 or so, there is actually an observable coming from the hyperfine spin flip transition, because the proton and the electron can either be aligned in a hydrogen atom or have opposite spin, and those have a different energy state, and going from one to the other produces a photon with a wavelength of 21 centimeter. So that in principle is possible to observe from redshift 200, and then after redshift 30 to 50, you get the formation of the first galaxies. Yeah, I'm going to draw a few of them, not all of them. It's going to be and that period is known as cosmic dawn. Yeah, cosmic dawn. Which will transition quite naturally into the period of reionization. And this is truly when the hydrogen, which was neutral up until then, reionizes until the universe is mostly filled of free electrons and free protons, yeah? Except for a few bound objects. And so reionization, cosmic dawn, is roughly between this end here up until redshift, well, 15 or so, 20. Depends a little bit on your preference. And then reionization is all the way to redshift 5. Okay? And then we have all the galaxies which you can now observe today in optical, for example, but also in other frequencies. And so we are here, yeah, observing all this. The main point of this image here is to say that I'm observing some field here, which could be the number density of galaxies or some other tracer of matter, and I want to relate that field to something that happened here. And so, as I said before, what we want to measure here is correlation functions of this field related to correlation functions produced at the end of inflation. Okay. And the same is true. Any fluctuations that we observe in the CMB are related to fluctuations that were imprinted at the end of inflation. Okay. Right. So now we're going to do a little bit more physics. This was all a lot of blah blah. So let's say that we have some fields. In this case, well, we have two. Well, yeah. So let's say we have a field that we call so our fluctuations in the cosmic microwave background, which you can denote as delta t over t. And now we write this as theta. So we use this quantity theta. And similarly for densities or galaxies or whatever, we call that delta rho. Yeah, some fluctuation in the density field. And then we know that during inflation, and if inflation was driven by some scalar field, again, we will get to that later on in lecture 3, we can denote that by phi. Yeah, and the fluctuations in phi are denoted as delta phi. And so the point here is that this is basically saying I have fluctuations in phi, they couple somehow to fluctuations in the matter and radiation field. So I have phi, and I want to go to theta and delta rho. But it turns out, at least that we know the way we formulate inflationary theory nowadays, is that phi does not couple directly to these fields, but it couples only to the metric, which you can describe as fluctuation in the metric as psi, and then they couple to the densities, the fluctuation in the density fields. And so what we need to know now, and so that's going to be the topic of tomorrow, is some kind of mapping between these two. Yeah, I want to know how my phi couples to these, and and for that I can derive, or if I can do that, I can derive a transfer function, which I'll later know, unfortunately, also by theta, but I'll just call it f now. So I have some field phi or delta phi. I should write delta phi here, and then that's related somehow with some transfer function to my observed field theta and delta rho are related to delta phi. So if I can derive such a function, or functional, then I'm in good shape, I think. And that will be the topic of tomorrow. And the main thing, of course, is that then the question is, are the statistical properties preserved? Yeah, so yes, maybe I can find such a mapping, but are the statistical properties of these of whatever is happening in the field driving inflation, are they preserved during this mapping? And it turns out, well, effectively I would say this is true when this mapping is linear. If this mapping is nonlinear, then some information could get lost or hard to trace. For the CMB, this mapping is linear, so that's very nice, right? So that's why the CMB is one of the most successful ways to constrain early universe physics, because this mapping is linear, and so none of the statistical properties is lost in the mapping, or very minimal information is lost. Okay, so for the CMB, this mapping is linear. Okay. For large-scale structures, so for the density field, it's not. And it's mostly because gravity ruins everything, yeah? That doesn't mean you cannot use large-scale structure, of course. We know that, we can use it, but it's harder, yeah? And you have to deal with the fact that at small scales, things become quite nonlinear, and therefore information is lost. Okay, any questions about this? Okay, so let's move on to this cosmological principle. Does anyone know what the cosmological principle is? Yes, go ahead. Yes. Homogeneous and isotropic. Yeah. Okay. So that's good. Why is that good? Is that a useful property? Yes. Yeah, in fact, so remember that what we want to do is we want to compute these correlation functions. Now, if it was a completely random field and there was there's no cosmological principle, this could be a very complicated function, right? But the cosmological principle really simplifies correlation functions. So think of these as symmetries, as we'll see in a second, okay? So let's say we have a random field. And of course, I'll denote this with phi. Yeah, and then phi could be a function of time and space. And this could have fluctuations. So there could be, so there's an average plus fluctuations. Okay? And what we want to compute is correlation functions of this object. Now, fixing time for the moment, we can write down a general two-point correlation function. So let's start with the two-point correlation function. And for simplicity now, I'm gonna drop this delta. It doesn't matter for now. Later on it does, but now it doesn't. So we have a two-point correlation function, which we define as such, of x and y. defined as the integral, the path integral over all possible realizations of this field, phi x and phi y, with the probability density of this field. Yes. Okay. And so in principle, this thing could be anything. This field, this probability density. And so we don't have to make assumptions about that now. And this really is very similar to the path integrals in QFT, which we just discussed in the previous lecture. But again, you don't have to worry about that too much at the moment. Now, the cosmological principle, as was just said, states that the universe is isotropic and homogeneous on large enough scales. In cosmology, we just work with large scales by definition. So it is homogeneous and isotropic. If it's not, then I don't think we can do cosmology. So let's stick with that. So if it's indeed, so this property then translates, cosmological principle translate to statistical homogeneity and statistical isotropy. So what does that mean? That means that, so let's call, I'm going to make abbreviations here, so I call statistical homogeneity with SH, and then I define statistical isotropy with SI. So for statistical homogeneity, it means that if I move from one place to another, the universe looks the same. And so that basically corresponds to translational invariance. Okay. So if I go to another point, another spatial point in the universe, it should have the same statistical properties. So I can apply my translational operator, which I call curly T, S on phi of x, and this is defined in such a way that if I move my spatial component by some other vector s, then it stays the same, right? So this, or at least if it's invariant on that, but this is what I mean. And then I can state that if I'm statistically invariant, or my statistics invariant under this translation, so I apply my translation to this field, so then I have that this has to be the same as this, right? Okay, so what does that mean for correlators? So my correlator, of course, when I apply two translations, be simply equivalent to x minus s, y minus s, okay? Clear? So if I have this, then I know automatically that if this has to be true, then my correlation function can only be a function of the difference of this vector. Yeah, because I want to make sure it's the same. So now the conclusion must be that my two-point correlation function, if a statistical homogeneity applies, then my correlator has to be a function of the difference between x and y. That's the conclusion. Okay, so that's point number one. So that already simplifies the possibilities, right, of your correlation function. Now, we can apply statistical isotropy the same way. So statistical isotropy is equivalent to rotational invariance. So with statistical isotropy, that's number 2. So we apply that, where we have some rotation operator acting on phi of x, and that's the same as phi of r, which I put with an underscore to differentiate with this r. So this is a rotation matrix operating on x. Sorry. Okay. So that's what rotational invariance means, or rotational, what a rotational operator does, and what rotational invariance then means for the correlator. Of course, we can apply the same logic. We apply it to the probability distribution for phi, but for the correlator, as before, it just means the following. Okay? So that needs to be the case. And so if you combine this with statistical homogeneity, so now we say Si plus Sh, we get that the correlation point function, the 2-point correlation function of x and y is the same as the rotational operator acting on x minus y, because we already said it has to be a function of only the difference if it's statistical homogeneous. And then it turns out that this means that the correlation function of x and y has or can only be a function of the modulus of the difference. Okay? So that has simplified the possibilities. The cosmological principle simplifies the form this 2-point correlation function can have. And in principle, you could do this for any correlation function and find similar simplifications. In the context of cosmology, we typically work, or you often work in Fourier space. So let's do that, just to see something similar happening. So in Fourier space, I write phi of k. So I usually use underscore here when I'm working in Fourier space, and when I work in position space or real space, I have brackets, right, for the argument, just for future reference. So this is equivalent to the integral, and we use the following notation. And the reverse. Okay, so that's our Fourier notation. Okay, so having this, we can apply the same as before. Statistical isotropy and homogeneity. Okay, so we have again let's see what I wrote. Yeah, so we now apply this operator again on phi of k, and this becomes dx by x minus s e to the minus ik x. Yes, and then we can rewrite that as follows: d3x prime phi x prime. And then we have e to the minus x e to the minus I k dot s. So, yes. Right, so we pick up a phase factor. Now we can apply this to the correlation function. So the correlation function is written as follows. The power spectrum, so we have phi k prime star. And that's given by, so if I actually do this, you get that this has to be the same as phi k, sorry, phi k prime star times e to the power minus I k minus k prime dot s. And so here you see exactly something similar happening. So this is for, again, this is for statistical homogeneity, which is that really limits the type of correlation function, the form this correlation function can have. In particular, this means that the correlation function or the power spectrum of phi of k has to be proportional to some function f of k times the delta function. Okay? And so statistical homogeneity in some sense tells you that modes are uncorrelated. In this case, k modes are uncorrelated. Oh, right, there must be a plus. No. No. We're applying it only to this field here, right? So we're pulling this field through? Yes. Yeah. Yeah, and that's the same as this thing. Yeah. Okay, so so that means that this has, and this can be some function of the vector of k still, right? So there's some freedom here left. But there is a delta function. Of course, the delta function has to be here, otherwise this will not be true. Yeah, so this has to be set to 1. Okay. Now we can apply rotational invariance. Okay. So again, we apply this vector r, this operator r on phi of k, and if we do that, we get that this is the integral of d3x phi r minus 1 x e to the minus I k x. And we can rewrite this as d3x still, but then we have phi r minus 1 x. And we rewrite this thing that what we do, we rotate both vectors. If we rotate both vectors, x and k, of course the dot product will remain invariant. Yeah? So we write this as e to the minus I r minus 1 k dot r minus 1 x. Yeah, so the dot product should remain invariant under this. And so this is defined as phi r minus 1 k. Oh yeah, sorry, is it too small? Tell me if it's too small. Okay, yeah, I'll try to write larger. Okay, sorry. Is this clear so far? Oh, it's R, the rotation matrix applied to vector k, dotted with the rotation matrix applied to vector x. And we assume. Oh no, they're both minus. They're both just rotation inverse rotation matrices. Yeah, and the point again, just to reiterate, we assume that the dot product remains invariant if I rotate both vectors by the same amount. Okay, so then if I apply both, right? So I combine again statistical homogeneity plus statistical isotropy. If I do that, I get the following. So I write R minus 1 on, sorry, let's write like this. Sorry, R on phi k. This is not the vector, this is the operation. R on phi k star prime is equivalent to what we just computed, phi r minus 1 k phi star r minus 1 k prime. And this, oh, be higher. This is equivalent to f, because we use statistical homogeneity, r minus 1 k delta r minus 1 k minus k prime, and this is equivalent to f of k vector delta k minus k prime. Okay, and the reason that this is true is because the delta function is the same as the determinant of the rotation matrix multiplied by delta k minus k prime, and the determinant of the rotation matrix is 1. Yes. Okay. And the next thing here, of course, is that now we have to say that my rotated vector of k, because these are the same delta functions, that means that my rotated vector of k, this function, is just f of k, and that can only be true if k, it's not vector k, but it's the modulus of k, right? So in the end, it comes down to, let's write it here. It becomes down to the fact that f of k vector has to be f of k, right? So without the vector, it's the modulus of k. So if we combine everything together, then we can write down the general correlation function of two, in this case, scalar fields, f of k, phi of k prime is given by 2 pi squared over k cubed, 2 pi cubed, delta k minus k prime, and then we have to find power spectrum phi squared of k. And we've introduced this 1 over k cubed, that if phi is dimensionless, then this thing is also dimensionless, this power spectrum. So we've now found an expression for the power spectrum. And all these constants, they are just there because of Fourier rules. Okay. Now, for most practical purposes, during these lectures, we will mostly work with this object. In principle, if we would have talked about large-scale structure, then we could also have talked about correlation functions in position space. For example, if you have read a weak lensing paper for example, then there's going to be correlation functions instead of these power spectra. And you can relate the two. Again, if you want to know about this, please check the lecture notes, where this correlation function is defined as phi x, phi y, and you can check, I have derived this in the notes, it's equivalent to dk over k of my power spectrum integrated against a spherical Bessel function. Okay. So this is my 2-point correlation function, and it's related to my power spectrum via this integral. But we will not work with this in this lecture series. What we do work with is angular power spectra. The CMB, of course, is we work on the sphere. We don't work in 3 dimensions, and we use spherical harmonics to do that. And so we write, again, as a definition, delta t over t is what I call theta in some direction on the sky. And this can be decomposed into spherical harmonics with spherical harmonic coefficients ALM against spherical harmonic functions YLM. And you can work through kind of the same exercise, but in this case, you only have to invoke statistical isotropy. And if you do so, you find that correlation functions of these spherical harmonic coefficients, which is typically what we measure when we do operations on the CMB, is given by the following. So if I take ALM prime star, these correlation functions are proportional to L prime, delta M prime, CL. And this is your angular correlation function, or angular power spectrum. Okay, and so the nice feature of this is that, so this is the only thing, there's only 1 degree of freedom, which is a scalar degree of freedom, which is L. That means that modes are, again, not coupled, right? It's similar to the fact that we had this delta function for k minus k prime, but here we have only one function. We have these Kronecker delta, which set 2 L's to be the same and the 2 M's to be the same. And that's true in a statistically isotropic universe. You can write down correlation functions to higher order, yeah, or spectra to higher order. When you have the bispectrum, you have 3 copies of these spherical harmonic coefficients, and the form of the associated bispectrum will also be conditioned by statistical isotropy. Okay, and you can look up how this is done in one of the many references I give. Okay, so that's clear. Now, of course, if you have, if there's anything that couples things non-linearly, this is no longer true typically. So then we get mixing. So then this delta L, this Kronecker delta L prime will not be there. And so people actually have looked at that, but we haven't found any evidence for that in the CMB. Yeah, at least at this level. There is some mixing just because of gravitational lensing. So lensing, of course, is a nonlinear effect, and that mixes these modes. But this, I think, is a very small effect, almost. Will, do you know how big this effect is? It's very small, right? You were not paying attention. Okay, never mind. He will tell you later whether this is a big effect or not. Okay, good. Now yes, go ahead. Yeah, sorry, this is a spherical Bessel function of the 0th order. Yeah, sorry. Yeah, we're not using it, but yeah. Say it again, is it? Yeah, so in the CMB we work, so in the CMB we never work with these 2-point correlation functions, the correlation function, and I'll tell you now why. Okay? Uh, the reason is quite simple, well, maybe not super simple, but I can write down a correlation function which I now call C, um, and this correlation function, so now will depend on two directions on the sky, and it's defined as theta n1, theta n2. This object, if you do the math, will be proportional to 1 over 4 pi. So you just fill in this power spectra and the definition of the spherical harmonic transform. And if you do that, you get that this is proportional to L plus 1 times CL times PL, where PL is a polynomial of order L, of cosine. You want to use theta, but maybe that's not a good idea. Small theta, 1, 2. And this small theta 1, 2 is the angle between the two normal vectors. And the main issue is, as you can see already, that here now these things are coupled through this angle. So they're no longer. So we had this very nice feature that these L's decouple, but the angles do not. And that's why typically. So if you would plot such a correlation function as a function of angle, different angles would be correlated, and so that makes it not a useful way to measure things. While in spherical harmonic space, you completely decouple every single L, and therefore each data point will be independent. Okay, so that was the main point that I wanted to make, and now we've learned how to get these correlation functions sorry, maybe I should go this way, in an isotropic and homogeneous universe, and they simplify tremendously. And even in the lecture notes, I show you can estimate the degrees of freedom that are relevant for these correlation functions. And that's a simple relation that you can derive. So in some sense, if you had no symmetries, right, any correlation function would scale as the number of points in your data in some sense. So if you had like a CMB map of n pixels, right, the number of combinations that you could do would scale like n squared. Yeah, but it's not the case, luckily for us. Okay, and the same thing would be for the 3-point function, n cubed, etc., etc. Right? But we get a very large reduction in the ways we can correlate things. So in summary, oh yeah, so there's one thing that maybe you probably have noticed during my my talk, which is that we talk about correlation, endpoint correlation functions, but then when we relate them to the Fourier equivalent, it's actually one step down. So you have the 3-point correlation function is corresponding to the bispectrum, which is a little odd, yeah? But that's just the way we, yeah, I don't actually know who invented that, but that's the way we work. So that can be confusing sometimes. Okay, so in summary, we wanted to learn about the early universe. The early universe is dominated by some mechanism where the most promising candidate is inflation. The assumption is that somehow inflation sourced the seeds of structure, sourced for the fluctuations that later turned into the galaxies that we observe today, or the CMB that we observe. By measuring correlation functions, either in the density structure of galaxies or in the CMB, we hope to learn something about the initial conditions and thereby learning something about fundamental physics. That's the logic. And we've learned now how to compute correlation functions in a universe that can be described by the cosmological principle. And the two, so if the universe is truly Gaussian, then the only thing that matters is the power spectrum. The power spectrum then, as said, only depends on L or K. Yeah, modulus K. So that makes it very nice. Okay. Any questions about this? All right. Let's all move on to the next part of this first lecture. So now, of course, we need to describe the universe. That's not easy, but it turns out that it's actually much less complicated than you might think. So on large scales, of course, the most important part is general relativity, and for general relativity, what we need is a metric. And so once I give the metric, I just have to do the magical math that we can do with GR and derive all the relevant equations. So that turns out to be literally what you have to do. Now, at the fluctuation level, of course, things become a little bit more complicated because we have to talk about interactions between the different species in the universe. So radiation and matter, they couple to each other. And so you have to write down the equations that govern those interactions as well. This by itself could be like at least 4 lectures if I want to explain that in detail. And so in tomorrow's lecture, I'll just give you the result and we squeeze everything together to get to the right answer. But for the background evolution, we need very little. We don't just need GR. Okay, so without further derivation, any book on cosmology will give you the derivation. So I'll skip that. And so typically we work with the Friedman, Robertson, Lemaitre, Walker Lemaitre metric, FRLW. FRLW metric, right? Which obeys the cosmological principle. So it's an isotropic homogeneous metric, and we also assume it's flat, so there's no curvature. And then it's written as follows. So space-time interval is given by a squared d tau squared minus dx squared. And we've introduced conformal time in the following way, where t sometimes referred to as cosmological time. Okay. And a here is a scale factor, and with that we can define Hubble, basically from the get-go. We're just going to define it. So the Hubble parameter h is given by the time derivative of the scale factor, where derivatives with respect to time I denote with a prime, and derivatives with respect to conformal time I denote with a dot. So this is a prime over a, and then I can define similarly a curly h as a dot over a. Okay, so this is my Hubble parameter. So it tells you the rate of growth as a function of, or in units of the scale factor. Change in the scale factor in units of the scale factor. So think about this as a relative speed of the growth of the universe. So next we have GR. So we have a metric. Now we can write down everything else. So in GR, of course, we have the G mu nu equals minus 1 half G mu R equals 8 pi G T mu. So this is a metric, which is basically, in this case, for the background, just a squared times diagonal, with 1 for time and minus 1 for space. And we relate that to the energy density to the momentum energy momentum tensor. So this part, of course, is the geometry. This part is the energy density. I'm sure that many of you have had GR, right? Kind of can assume that. So I don't have to go to the details. Not that I have time to go to the details of GR, but just in case. Of course, then the only thing we have to compute now, given the metric, is the Christoffel symbols, and then the Ricci scalar and the Ricci tensor, etc., right? To get to the proper equations. And of course, we need the prescription for the energy momentum tensor. So I'll leave it up to you to go through the details, but again, they are given in in the lecture notes. So we have the Christoffel symbols, which are given by G mu gamma G gamma beta sorry alpha gamma comma beta mine plus G beta gamma comma alpha plus G alpha beta comma gamma. Yeah, so you have the Christoffel symbols, and we have the Ricci tensor. Anyways, look it up in my notes. The main point here is that we can compute all these, and again, I leave that as an exercise, but I'll give you the answers. Just taking the metric that we have, and what we find is that the only non-zero components of G are G00, which is given by minus 3h squared, and we have Gij, which is given by 2/3, oh sorry, R00, is that right? Minus h squared delta ij. Okay, so you can convince yourself later that this is true. Now, the next thing we have to add is the energy momentum tensor. Yes, and in an FRLW metric for a perfect fluid, which we can assume, it's given by, so T mu is given by rho plus P, where rho is the energy density and P is the pressure, times the velocity plus P G mu. And the fourth velocity is given by dx mu d tau. And if you are a co-moving observer at rest, then this object is given by 1, 0, 0, 0. Yeah, and of course when you lowercase, when you have a lower index, there's a factor of a you pick up. Okay, so we also know that the energy momentum tensor, or the energy momentum, is conserved. So that tells you that the covariant derivative of T mu nu is 0. And if you compute, if you then take the nu equals 0 component of this equation, so just do that for yourself, then you find that the time derivative of rho plus 3h times rho plus p equals 0. Okay, and so this tells you, this is the energy conservation equation in an expanding universe. Of course, it's different from a universe that would not be expanding. Okay. Then we have to go on and introduce the so-called equation of state, which tells that there's a relation between the pressure and the energy density. Anyone familiar with the equation of state? You've seen it before, probably. So we know that P over rho is proportional to W. And that tells you that if you use the energy equation, energy conservation equation, that rho has to be proportional to A to the minus 3, 1 plus W. Okay? And I'm just going to tell you that because, again, there's only so much I can derive. But WR, so for radiation, is a third. W matter is 0. And W lambda, which is the cosmological constant, is minus 1. Okay, so now we have all the relevant stuff in here to derive the so-called Friedmann equations. Before that, let me. Oh yeah, no, we can. We are going to do that straight away. Okay, so if we now use the Einstein equations, right, for GR, we can show that the 0,0 component of that equation leads to the following relation: h squared equals 8 pi g over 3 times the energy density. Yeah. This is a key equation in cosmology, and it's usually called the first Friedmann equation. Okay. Now we can also take the ij component of the Einstein equations and find that a double prime over a equals minus 4 pi g over 3 rho plus 3p. Okay? And this is sometimes called the second Friedmann equation. Okay, so I would say for cosmology, these are probably the most important two equations that govern the evolution of the universe. They relate the geometry, which is basically covered by this factor A, the scale factor, to the energy densities and the pressure, right? That's what you see. So there's always some relation between the scale factor and the pressure and the density in both these equations. Any questions about this? Okay, let's move on. So now it's useful to define this thing called critical density. Note also that, again, we have assumed a flat universe, so that means there's no curvature, no spatial curvature. If you do that, the equations will change a little bit, and you get an additional degree of freedom known as the curvature K, and that will change a few things. But I think, we don't have any evidence for spatial curvature, and so I set it to 0, and I think it simplifies a lot of the things that we're about to do. But in principle, it's straightforward to include it, and any textbook will do it for you. So now we're going to find the critical density in the following way, as 3h naught squared over 8 pi g, where h naught is the current value of the Hubble parameter. So we say naught because it's today, I guess. And this is equivalent to about 1.9 times 10 to the minus 29 h squared, small h squared, grams per cubic centimeter. And that is roughly 10 to the minus 5 protons per cubic centimeter. Now, that's assuming that h, small h, is of order 1. And in fact, it's 0.7. Yeah, and the Hubble tension, who has heard of the Hubble tension? Probably everyone, yeah? So that just tells you that there is a discrepancy between this parameter being either 0.67 or 0.73, something like that, 72. Okay. So given these numbers, we can, or giving this critical density, I can also define omega for any species as my density of a species over this critical density. Yeah, so I could be radiation or matter, for example, or lambda, if you will. And if I do that, I can rewrite my Hubble equation, my Friedmann equation, or my Hubble parameter. Okay. I can rewrite my Hubble, Friedmann equation as h squared equals h naught squared times omega r, a to the minus 4, plus omega m times a to the minus 3, plus omega lambda. Okay? And so here, now you might ask, okay, what's going on here? Right, so the radiation decays as a to the minus 4, and matter, as you can might imagine, the energy density decays like 1 over a cubed, which of course is just because of the volume factor, right? So the universe grows, and then each and every direction scales by 1 factor of a, and so decreases like 1 over a cubed. The cosmological constant is named cosmological constant because it doesn't change as the universe grows, right? So that's why there's no a dependence. In principle, you can also, of course, if you want, and you're more like, oh, I'm a person that wants to check phenomenologically what happens. So of course you can add terms that scale like a to the power minus 1 and a to the power minus 2, yeah, and then see what that does. And I think people have done. So curvature scales like 1 over a squared, in fact. And I don't know of anything that scales like 1 over a, but somebody should tell me if there is. Okay, so where is this additional? Now the question becomes, where does this additional 1 over a come from? And who knows? Who said what? Yeah, but why is that there? Yes. So of course this is the energy of the photons, and their wavelength will be stretched in an expanding universe, and they will lose energy. And we can actually derive the energy that they lose from first principles. So we can do that, and that'll be the last part of this lecture. Photons in an expanding universe. And again, the reason why I focus on photons is because later on, right, our goal is to derive this transfer of initial conditions to an observable, and the observable of choice is the CMB. So we want to know how phi relates to this theta. And this theta, of course, is the fluctuations in the radiation temperature. Okay, so for photons, as you know from either your special relativity class or your GR class, they're massless, because everybody knows. But that means that the modulus of their 4 factor, which is m squared, is 0. And that, and of course, we've learned that photons who do not, if there's no additional forces available, then objects move along geodesics in GR, and that's the same is true for photons. So propagate geodesics if no external forces. Okay, and so we can write down geodesic equation dp mu d lambda equals minus the Christoffel symbol mu rho, or nu rho p mu p rho. So again, this is the 4-factor p, okay, just to be clear. And so this equation is kind of equivalent of saying dx squared dt squared equals 0 for Euclidean space. And lambda, the defined parameter, is defined such that p mu equals dx mu over d lambda. Okay. So what to do now? Of course, now we have to write down p, which we can. So p, of course, the energy of the energy of a photon and its momentum, string momentum, are identical. Otherwise, the mass is not 0. So you can write down p mu as E, comma E, I hat. Yeah, so the fact that it's the same, the three momentum is the same as the energy, and so we can rewrite our affine parameter derivative as dx naught d lambda d lambda dx naught. Is that right? Sorry, dx naught equals e d dt from this, and then the 0 component of the geodesic equation tells us that E dE dt equals, sorry, minus the Christoffel symbol ij0 pi pj equals delta ij h a squared pi pj. And then if I fill in the right Christoffel symbols and use the fact that g mu p mu is 0, this then becomes minus e squared plus delta ij a squared pi pj equals 0. And that tells us that 1 over e dE dt equals minus Hubble. Okay, so yeah, this is my last equation. So I should use 10 minutes to explain this last equation. So does this make sense? Maybe. If you say yes, you're probably right. Well, it makes sense because of what we just had. So I can write this equation, or you can solve this equation. Okay. So this means we know that h is just dA over dt times 1 over a. Okay, that's how we defined h. Yes. I'm following my notes, so it could be that I made a mistake. Um, can you point out where I'm wrong? Oh, which one? This one? No? This. So this has to be equal, is what you're saying? Okay. Yeah, could be true. So it's okay? Yes, yeah. Okay. Okay, yeah, so the final point here is that I want to use this, so that means I can rewrite the following equation. So I have 1 over E dE equals 1 over A dA, or minus 1 over A dA. And so if you just do the integral, you'll find that E is proportional to A minus 1. And that's exactly what we just said, right? So the fact that the energy of a photon redshifts, and therefore it should scale like 1 over A. But this implies, of course, that rho r scales like, which is really E over V, yeah? So this then scales like A to the minus 4. Okay. Any questions about this? And some of the steps that I went over quickly, they are derived in a little bit more depth inside the lecture notes. But I think we've, well, so in summary, I think we now know roughly, at least at the background level, what happens in an expanding universe, how energy densities are related to the scale factor. Of course, so that tells us something about the evolution, it tells us something about Hubble, which is relevant. But the next step, of course, is perturbing the universe, because we want to look at fluctuations. And if we perturb the universe, then in principle, we just have to perturb the Einstein equations, which means that we both get perturbations in the metric, and we also get perturbations in the energy momentum tensor. Yeah, so we have to just perturb both sides. And in principle, you could also, well, and this could be rather complicated, of course, because there could be tensor, vector, and scalar perturbations. But as I'll explain a little bit tomorrow, there's the so-called theorem which tells us that these fluctuations decouple at linear order. And so that's a very nice feature, which means that I can literally only focus on scalar perturbations and forget about the vector and the tensor perturbations when I do this. So that would be the Einstein equations that I have to perturb. And then in principle, of course, there's also interactions, which I have to add now, right? Because particles and fluctuations interact. That, again, would concise an entire week to explain all the details of that. And so I'll just give that as a final result. We combine those two, and we compute how fluctuations in the initial density field or the initial curvature translate to fluctuations in the photon temperature field. And that allows us to derive these linear transfer functions. Yes? That there are no questions, then this will be the end of today's lecture. Oh, yeah. Yes. Yeah. No, the sigma A tension. Okay. So we can infer, so sigma 8 is a measurement of the amplitude of fluctuations at a fixed scale. So it's similar to AS, but then evolved forward, because we measured this in large scale structure. And I think the measurement that we get from measuring the CMB and then estimating what this value is versus the measurement we can get through cluster measurement. Is that Will? That's correct, Will? Sigma 8. The tension is between the measurement of clusters and the measurement of Planck, right? Gravitational lensing and Planck, yeah. So you can infer something, because the amplitude of fluctuations will affect how photons get lensed. Yeah, and that means you can infer what this amplitude should be based on lensing measurements, and then you can infer it directly from the CMB, and those two do not agree. So that's the tension. But I think that tension has weakened a little bit, yeah. And it's solved by what? Baryon physics? Yes. By astrophysics. We solve it by astrophysics. Any more questions? Okay, yeah.